Good morning. In this section, we're going to study another probability mass function. And in this one, what we're going to do is we're going to study some random event which occurs over time or over a geographic region. And we're interested in the number of times our event occurs. So as an example, we want to count the number of cars, so that's the thing we're counting, which pass through an intersection per hour. So we're counting this. So we could ask, hey, what's the probability that 2 cars pass through the intersection in an hour? So again, we have 2 things going on here. We have this discrete thing we're counting. It will be a discrete distribution, but the fabric under which it lives is continuous. In this case, time. And again, another one is geographic. So you could ask, for example, number of sharks per square mile. That would be another example. So how are we going to do this? Well, let's look at our hour. And let's say a car passed through the intersection at those different times. Well, what I could do is I could break this hour into n subintervals. And in each of these subintervals, a car either passes through the intersection or doesn't. So each of these subintervals is Bernoulli, so that this entire thing is binomial. Well, this is, however, within n subintervals. So I could think of that, n could be 2, for example, and then it would be 30-minute blocks. But I'm not interested in that. I want to be thinking about it throughout this continuous interval. So what do you do if you want a continuous interval? What do you do with your n, with the number of subintervals? Well, thinking back to integral calculus, what you can do is you can take the limit as the number of subintervals approaches infinity. So this distribution we're going to study is the limiting distribution of the binomial distribution. So let's see how that would work, and let's derive the distribution. First, I'm going to let a lambda be np. There's going to be a reason for that later on. This is the mean of my underlying distribution. Then I'm going to take the limit as n approaches infinity of this distribution. So it's n choose x. My p is lambda over n, so lambda over n to the x. 1 minus p, which again is lambda over n, to the n minus x. All right, we need to compute this limit. That's our goal. So the first thing that I want to do is let me expand a couple of things out, which will help me to derive this. So let me write that as n factorial over x factorial times n minus x factorial. Let me write this as lambda to the x over n to the x. So I'm just expanding that out. And let me break this guy apart. So we get 1 minus lambda over n to the n times 1 minus lambda over n to the minus x. So I'm taking all of those pieces out. All right, so couple of things that we can do here. Firstly, this lambda to the x and x factorial have nothing to do with n. So I can pull those guys out. So this is lambda to the x over x factorial. I'm just pulling them out. And then I have the limit, n goes to infinity. Let's see, n factorial over n minus x factorial, n to the x, 1 minus lambda over n to the n, 1 minus lambda over n to the minus x. All right, so we know from calculus that the limit of a product is the product of the limits as long as those limits exist. Almost sounds like a nursery rhyme. So let me study each of these guys separately. I'll start with the easiest one, easiest for me anyway, and we'll move on to the toughest one last. So let's check this guy out. The limit as n goes to infinity, 1 minus lambda over n to the minus x. So I want you guys to actually try that one. Pause the video, give that a shot. All right, hopefully you said, well, n's going to infinity, so this guy's going to 0. 1 to the minus x is just 1, so that limit is 1. Beautiful. So this guy here is just 1. All right, let's study this one. The limit as n goes to infinity. Well, first off, if I simplify this, then that'll become n times n minus 1, times n minus x plus 1. So I'll let you guys try this on your own. Put in a couple of different values of x, and you'll see that stuff cancels out, and you're going to be left with this on top. So let me also say that n to the x, I can think of that as n times n times n times n. I've got x of these guys. Well, let's see what happens here. If x happens to be 2, then the final term here is n minus 2 plus 1. The final term is n minus 1. So it would just be n times n minus 1. So we have 2 terms, right? Because the bottom would be n to the second, or n times n. If x equals 3, it would be n times n minus 1 times n minus 2. And we would have n cubed on bottom. So my point is that for every term on top, I've got a term on bottom for all these guys. Well, as n approaches infinity, n over n approaches 1, n minus 1 over n approaches 1. Gosh, in fact, all of these guys, n minus 2 over n approaches 1. All of these approach 1. So guess what? This limit is 1 as well. I love this distribution. Okay, so you may need to think about that. Pause the video if you need to. So now let's study this guy. So I want the limit as n goes to infinity of 1 minus lambda over n to the n. Well, to help me understand what's going on here, I'm going to make a variable substitution of minus lambda over n. Well, if that's the case, then let's see. First off, this tells me that n is minus lambda over m. So let's see. If n goes to infinity, this goes to infinity, I guess m, let me do it this way. If n goes to infinity, m must be going to 0, so that's first off. This becomes 1 plus m, and n is minus lambda over m. Well, to help me get a better handle on that guy, let me write that better. M is going to 0. Let me use a property of exponents, which says I can rewrite minus lambda over m as as 1 over m times minus lambda. And then we actually have a property of limits, which I have to be honest, some of you might know this, some of you might not. I don't even think I teach it in Western's 124 class. But basically, what we can do is we can, if we have an exponent up here, we can nudge the limit inside. So finally, what is this limit? Pause the video, see if you can reach into the recesses of your mind. You've actually seen that limit, I am sure of it, in another class. All right, hopefully you said, oh, that's just the definition of our good friend E. That limit is E. E mysteriously pops up everywhere when you least expect it. So I guess this guy here is e to the minus lambda. So we have now derived the limit of that distribution. So I guess we get that our distribution that we're interested in to model this, namely counting the number of cars that pass through an intersection per hour, is, and I'm going to rewrite it in the order it's typically written, e to the minus lambda, lambda to the x over x factorial. Mind-blowing. Out of the binomial distribution comes e to the minus lambda, lambda to the x over x factorial. I'm shocked every time I do this. This is known as a Poisson distribution. That's as good as my French pronunciation gets, so I apologize if it is très mal, but that is a French word for fish. Lambda is the parameter there. Let me also say that this guy has a new type of sample space that we haven't seen in action yet, which is a countable sample space, countably infinite. We could have 0 cars, 1, 2, up through an infinite number. Now, I know what you're saying. No, you can't have an infinite number in reality. Yes, you're correct, but this will still be a really good theoretical model. And in fact, if you back up here, where I'm taking this limit as n goes to infinity, since cars actually have length, this is not 100% accurate in terms of what's going on in the real world, but it's shocking at how well the Poisson distribution can actually model what you're looking at. All right, so a couple of things about this. Let's find the expected value of this. Well, we need to sum over the sample space. So I'm going to sum from 0 up to infinity, x times e to the minus lambda, lambda to the x over x factorial. So I want to talk about that infinity for just a second. Most students haven't taken infinite series before they've taken this class, and you don't need to. So I need to actually explain what this infinity up there actually means. Because the thing is, you can't add up an infinite number of things. It's impossible. You'll never be done. But what this actually means, if you see a little infinity up there, it just means that you're going to take the limit as n approaches infinity. So what this really is the limit as n goes to infinity of this sum. So you're computing that sum up to n, and then you're asking what happens when n goes to infinity. If that seems a little strange, I would invite you to revisit improper integrals, which played the same game. When you integrated from 0 to infinity, what you did is you took the limit as the top value went to infinity, but you were actually integrating a finite region. Okay, so I just want us to remember that this infinity actually means we're taking a limit. Well, let's play the same game that we've played before, which is, let's see, the 0 won't matter because 0 times stuff is 0. X over x factorial. X over x factorial is the same thing as x minus 1 factorial on bottom. If you expand out the x factorial, you can cancel out one of those x's. And once again, let me ask myself, what do I think the mean is? Well, let's go back to our derivation. I let this lambda equal n times p. That was the mean of the binomial. Well, if we have more and more subintervals, don't we think that the mean should still stay the same? Yeah, I would think it would. So I'm going to guess that the expected value is lambda. And by the games that we played before, that would mean I'll pull the lambda out, which I can do as long as I write this as x minus 1. And then my hope is to recognize this as another Poisson distribution. Well, the final part of the game was to, once again, convert this into something that starts at 0. I'm hoping to get 0 to infinity. So if y is x minus 1, then y is equal to 0 down here. Hold off on the bound up here for a second. E to the minus lambda, lambda to the y over y factorial. I'm just substituting in. And then again, if we understand that this infinity is actually just representing a limit, then if I bring every index down just by 1, I'm still zipping off to infinity. So this bound actually stays the same. It's still infinity. Then once again, almost by magic, this monstrosity disappears and is just 1. So we've just proven that the expected value of the Poisson distribution is lambda. And again, to me that makes intuitive sense. That's what I want to say about that. And, so the variance, which we're not going to prove, happens to also be lambda. Again, that will have some more meaning later on in the work. Okay, let's do a couple of examples with this. So, example, so cars arrive at a light at an average of 3 per minute. Let's say we assume that probability, the Poisson distribution holds. So let's do some probabilities. So 1, what's the probability that x equals 4? 2, the probability that x is bigger or equal to 1. And 3, what's the probability that x is 5 in 2 minutes? All right, you're welcome to try these. I'm not saying any of these are easy or difficult, but this is definitely the easiest. A little bit harder and definitely harder. So pause the video, give it a shot, and then we'll go over it. All right, hopefully you gave it a shot. So once again, let me put I shouldn't have erased the distribution. It's e to the minus lambda, lambda to the x over x factorial. So the probability that x equals 4, we just need to plug in our values. So an average of 3 per minute. So that's telling me that lambda is 3. Okay, we want to know the probability that there are 4 in a given minute. That's just going to be e to the minus lambda, lambda to the x over x factorial. And that's it. The probability that x is bigger or equal to 1, we can actually do 2 different ways. Well, first off, if it's bigger or equal to 1, then we can sum this distribution from 1 to infinity. And we get e to the minus lambda, lambda to the x over x factorial. But that's not very satisfying. Instead, I think a better approach is to realize that the probability of being bigger or equal to 1 is 1 minus the probability that x is less than 1. In other words, 1 minus the probability that x is just 0. Right? Because if x is less than 1, then x is going to be 0. All right, so so let me just be clear about this. If x is bigger or equal to 1, then that means that x could be 1, 2, 3, 4, etc., etc., etc. So the complement of bigger or equal to 1 in this case is going to be less than 1. All right, so doing that, we see that this is 1 minus e to the minus lambda, so e to the minus third, 3 to the x, which is 0, over 0 factorial. And 3 to the 0 is 1, 0 factorial is 1, so we get 1 minus e to the minus 3. And that's it. All right, this one's interesting. So now 2 minutes. Well, let's see. Now we have to remember how we're actually deriving this thing. And the way we're deriving it is we're thinking of the initial time frame as a binomial distribution with a particular lambda. Well, if we know that lambda is 3 on a per minute basis, what's the correct lambda for this new distribution? This isn't going to be the same exact distribution. What's the correct lambda? Well, the correct lambda is going to be 6. So this guy is distributed as a Poisson distribution with parameter 6. This is the mean on a minute basis. This is going to be the mean on a 2-minute basis. So we then have e to the minus lambda, lambda to the x over x factorial. And that's it. So in summary, the Poisson distribution is the limiting distribution of the binomial distribution. It's used to model events where you're trying to count the number of occurrences over some continuous interval. So thanks for listening, and I will see you next time.